Hello everyone. So we'll start the tutorial on from Katherine Kuchenbecker on creating interactive haptic robots. So I hope everyone can hear me. So Katherine is addressing one of the most difficult problems in robotics. So her work goes much beyond grasping and is in understanding contacts, the physical contact between robots and objects. So this is a problem that is involved in many challenging skills that are completely the state of the art on robots nowadays. So understanding contact would be something necessary to do precise handicrafts on industrial tasks like soldering or sanding, and other tasks like surgery. All these tasks involve a precise tactical understanding that only humans can do it. Until we get to a human level, I know Katherine is helping us understanding how we can do it through developing new haptic interfaces to enable teleoperations and to help with doing a physical human-robot interaction. So she currently is directing a center on the topic at Max Planck. So before that, she did a great career in the United States, where she got several prizes, and she was very active in the community, organizing several events and focus groups on the haptics. So I'm very happy and interested in hearing what Katherine is going to teach us, and I hope everyone enjoys. And Katherine, you can start.
Thank you so much, Manuel. As Manuel said, I'm Katherine Kuchenbecker, and I'm really happy to have the opportunity to deliver the first tutorial here for CoRL 2020. I want to start by thanking you, the audience, whether you're here in Zoom with us or watching on the live stream or watching the recorded version later. Really appreciate your attention. I will do my best to try to teach you some of the things I've learned that might be helpful or interesting to you. I want to thank the organizers for giving me the chance to talk. Claire Tomlin was actually one of my professors at Stanford and was a great inspiration to me, and I've known the other organizers as well for a long time. I want to thank other people who've mentored, taught, and collaborated with me and worked with me over the many years that I've been doing haptics and robotics research, people who've reviewed our papers, written letters, reviewed our grant proposals, and funded the work that we've been able to do. For this tutorial today, I want to thank three people in particular, and they are Jonathan Feeney, Georg Martius, and Alexis Black, who at various times, including recently, have given me a lot of input and ideas on the kinds of things that it takes to create interactive haptic robots. So I just really want to thank them for their support and input. So I showed this title slide, and Manuel was telling you creative interactive haptic robots, but what is that? So let's look quickly at some definitions from the new Oxford American Dictionary. Interactive means allowing a two-way flow of information. Here, especially between a human user and the system. It could also mean interactive with the world or other entities, other agents, other operatives, maybe another robot. Haptic, which is where I focus most of my career, is about the sense of touch, whether it's tactile sensations that you feel in your skin, which is throughout your body, or proprioception, which is more in your muscles and your joints and gives you an awareness of where your body is. Now, you probably already know robots don't have a great sense of touch, especially not a great tactile sense yet. They tend to have a decent proprioceptive knowledge of their physical body. And last, robot. I think all of you have a pretty good idea of what robots are. They can take many forms, but they're doing things in the world. Now, to get you motivated, before I try to teach you some of the wisdom that I think might help you if you want to create interactive haptic robots, I want to show you some examples, because I know you come from many, many different fields, and especially more learning-focused fields. So just to get you interested, here are 4 different kinds of haptic robots that my team and I have investigated over the last 18, 20 years. We'll just go through them in order. I'll just show a few videos for each category. So first, in social physical human-robot interaction, here the robot is interacting with you like it's another person almost. At the upper left, this is my first PhD student at Penn from the Grass Lab. He interned at Willow Garage, And he built this demo PR2 props that lets the PR2 exchange hand claps and fist bumps and fist bump explodes. And it's doing these by moving through a trajectory and then feeling the contact and reacting. And that tactile reaction was really, really important and amazingly fun. At the upper right, my now PhD student, then master's thesis student, Alexis Block, turned the PR2 into a hugging machine. And of course, here it is in the default form. Then she made it soft and warm and tactily reactive. And it can actually give really good hugs. We need more hugs in life these days. Then my PhD student at the time, who's now an assistant professor at Oregon State, Naomi Fitter, worked on rhythmic physical human-robot interaction. It's really fun to exchange hand claps with a robot. We played lots of different games with how the robot would react. And then she turned them at the bottom right into a series of 8 exercise games, which we recently published in JNER to get younger and older adults physically interacting with this embodied agent, often involving contact and stretching and reaching. The boxing one is really fun. Those are some social physical human robot interaction examples. Now I'm going to move to tactile robotic manipulation. And that is where now, instead of interacting with a human directly, the robot's interacting with things in the world. We saw some examples of this in Antonio Picchi's keynote right before this morning. This is a long time ago work, also Joe, Transactions on Robotics work, where we use just the native inbuilt tactile sensors in the PR2's hands, which are really primitive, just like 15 little pressure cells and an accelerometer, but we could still grasp and let go of and hand over objects. And then we knew we needed better sensors. So we installed the SynTouch BioTags, which are biomimetic tactile sensors in the fingers of our PR2 robot at Penn. And through a project called the DARPA Bolt Project, we taught the robot how to describe objects with words. Now it's painfully slow, but eventually it will grab that object and squeeze it and stroke it. And through simple machine learning, be able to describe it with words like that's smooth and crinkly and compact. And then at the bottom right, just to preview, we're working on a lot of other tactile sensing technologies. This is a flat sensor, so not yet on a robot body, but they can feel pressure at many points across the screen. This is work across its surface, work led by a postdoc, a research scientist in my team, Hyo-Sung Lee. And it works really well, and it's super fast and can feel a lot of context across a large surface. So that's tactile robotic manipulation. Now we get to haptic teleoperation. Here now the human is controlling the robot. So we're not looking at the robot to be very autonomous. We simply wanted to do a task in a remote environment or deep inside a patient. So we did a lot of work on robotic surgery and how to add tactile feedback. Here we put accelerometers up on the robot arms of a Da Vinci robot, and then we play those vibrations for the surgeon's hands left and right. This is actually a resident practicing, and they're not very good. We later were able to show that these haptic signals that we can measure and that the robot can feel are really indicative of surgical skill and give us a new avenue for training and helping surgeons master eye-hand coordination. We also proved that the technology works in real surgery. This is a pig where a surgeon was using the technology in an animal for the very first time, and we validated we could indeed measure really good haptic signals when there are transients. So when there's making and breaking contact, adding force feedback in such systems is really, really difficult. We've also worked, as you can see on the lower left, this is palpation. So again, surgery, we have a biotach moving across a soft object that has a rigid stick embedded in it. And you can see the platform under the operator's finger is tilting in different directions. And we're actually in real time mapping the tactile signals that that sensor is feeling into actuator commands for the operator to feel an approximation, like a tangent plane and a indentation of what the robot's feeling. And then at the bottom right, Rebecca Kershid, who's now an assistant professor at Boston University, built a very lightweight wearable device with motion capture that lets you pick up an object through the PR2 and feel making and breaking contact, grasp force, and vibrations. And in all of these scenarios, we've shown the haptic feedback helps people. So last of the 4 main categories of interactive haptic robots I wanted to get you excited about is haptic virtual reality. So here, instead of having a remote environment, the user is interacting with some model or trying to get them to make some movement. At the upper left, this was a fun project. Andrew, Stanley, and I made some wearable devices that try to guide you, try to tell you which way to go, and not through buzzing or vibrations, but actually like tapping on you or stroking on your skin. And so here you can see I'm following a trajectory as it's trying to make me move my arm. At the lower left, this is some beautiful work done by Heather Culbertson, who was my PhD student and is now an assistant professor at USC, where it's called haptography, where we modeled using data a lot of different surfaces and then rendered them through this commercial haptic device, an Omni, which is like a lightweight robot arm that you move around. Plus, that you see that little copper coil on the handle, that's a voice coil actuator, similar to what we were using in the surgical system, to let the operator feel the fine vibrations. And we also have hardness and friction, so we can vary how surfaces feel physically and really emulate how they feel. At the upper right, this is more of a fun project. So we're watching the user's movement and how they have vibration motors on their elbows and knees, and we let you feel what it would be like to be a robot for entertainment purposes. So you feel as though your arms were grinding and vibrating like a robot. And the bottom right is work with my PhD student who just defended, Eric Young. He created this amazing device called the Frappeteer that has 8 soft wires that are pushed and pulled to reposition this platform against your finger to make contact at the correct position and correct angle, and even prevent shear. So it's a 6-stop fingertip haptic feedback device, and you can see it being used there to touch virtual surfaces. So those are some examples of what I mean when I say interactive haptic robots. And I wanted to put this up front, hopefully to get you interested and excited, and think, okay, those kinds of things, those could be exciting. That might be fun to play with. Maybe even more importantly, it could be useful. We are looking at many applications in medicine and rehabilitation, in everyday devices, in cell phones, in household robots. The last thing you might think, once I make a video and show it to you, it looks really easy, right? Like, of course, the robot's doing that. It's picking that thing up. It's setting it down. The thing is vibrating the way it should. The signals are all happening in the way they should. And I think it's really actually not easy to create these things. Creating these interactive haptic robots, it's really difficult. And it's difficult, especially when you're starting, when you're first doing this, and it stays difficult throughout your whole career. You're always trying to assemble new things and do new things that have never been done before. You're building one-of-a-kind systems that no one planned to put this sensor and this actuator and this soft thing and this computational algorithm together. And there's like a million ways that it can go wrong. And so it's the human element, it's also the mechanical, the electrical, the computational components, the physical contact. It's incredibly complex, and that makes it interesting. I learned a lot of what I'm going to try to tell you today through my doctoral thesis and at Stanford, and then also later working on haptic interfaces. And so this is, like I already showed a different example, this is like a little lightweight robot, back drivable, that sits on a table and you hold the end and move it around. And so you're contacting it, and then you directly feel its mechanics, and then the electrical, the sensors and the actuators, all the way into the code. There's usually a servo loop running at 1,000 hertz, 1,000 times a second, checking with the remote environment or the virtual environment to calculate what you should feel, and then pushing that back out to you. And when it works well, it can feel seamless. And if any one thing isn't working, it feels terrible, or can feel quite bad. And I think basically haptic interfaces gave me these insights, because when you're using them, you're basically like dancing with the robot. Every little bad aspect of it is immediately perceptible, and it's this dynamic interchange, whether it's a social agent or a non-social agent. And so anyway, if you're interested in haptic interfaces, you can read this encyclopedia article that I wrote a couple years ago in this really nice Springer Encyclopedia of Robotics. There are many other great articles in there that I would recommend, and I go through different kinds of haptic interfaces. But this is actually not what I wanted to teach you about today, because I think this is a topic that only some of you might actually directly deal with. If you are interested, though, especially in grounded haptic interfaces, you should check out Haptopedia, which is another project in my team, where we've canvassed the literature and are sharing all these different, it's like a database, a taxonomy of haptic grounded force feedback devices. And I'm really excited about this in general to help advance research and innovation in haptics. But instead of telling you about these kinds of things, I want to try to teach you some more general lessons about creating interactive haptic robots. And that's because I've had many wonderful students and collaborators and postdocs. And you might think, okay, I'm going to create a new system like Katherine's describing. And you're going to find out it probably will fail. It probably won't work. It probably won't work the way you expect it to. And you might then conclude that you're too stupid. You shouldn't become a roboticist. You've made a bad career choice. You should go get a different job. And this is actually something Georg Martius, when he and I did this debugging research workshop a couple of years ago, he really impressed this on me. And you should not make that conclusion. That's the wrong, that's the wrong inference. Newly created complex systems, they basically never work the first time. And every one of these videos that I showed you, there were like 100 demonstrations behind the scenes where things sucked and they broke and they didn't work and they failed. They might have even like damaged themselves or just never even turned on. Like there are intricately many ways for them to fail. And that's frustrating and that's natural. And there are some techniques that you can use to make it easier to make progress and to get really good performing systems. In fact, you need to understand all the interacting elements in order to get the performance that you probably want. Okay, now I hope some of you are interested. And for the others of you who are sitting there saying, hey, okay, fine, but I don't want to create interactive haptic robots. I'm working on self-driving cars, or I'm doing a helper robot for something else. I'm not interested in this. And I hope I can convince you that the complex systems that I'm talking about, most of what I'm going to say today, it could be many things. It's not just necessarily haptic robots like this. It could be a software pipeline for vision or machine learning. It could be a robot controller. It could be a physical measurement device. It could be a manufacturing process or the files you're trying to compile for your CoRL paper or your own laptop or a video conferencing system like Zoom. Any of these modern technologies, I mean, some of them have physical components and some of them have less than physical components, but they always have room for complexity. And I think the kinds of skills that I want to try to share with you, some strategies, I hope would be useful for any of these. So even if you're not interested in haptic robots, maybe I'll still be able to offer you a couple interesting things from my experience. And then you should be sitting there saying, okay, what can I do? You showed me all these videos. I want to make things like that, or I want to make other cool stuff. Who doesn't? I want to contribute to society. I want to help the world. So I want to present to you 6 strategies, and I'll just go through them quickly. They are to think actively, to plot, and plot some more, to get help, to demo broadly, to prepare for the unexpected, and be positive. And I made these 6 categories by writing tons of little ideas on little cards and then clustering them and trying to arrange them in an order that might make sense to you. I was asked to leave time for questions throughout. So I suggest I take questions after number 1, think actively, which is this next piece I'm going to do. Then I have a lot to say about plotting with a lot of examples. So we'll do a second set of questions after point 2. And then 3 through 6 are pretty fast. And so I'll just do questions there before my final wrap up. And if that's okay with you, I think we can jump in to the next, to number 1. So point 1, I would like to persuade you to think actively. And what does that mean? This is a kind of crazy haptic device we built many years ago with a gyroscope that's spinning, and we're reorienting and trying to use that to create ungrounded haptic feedback. It has motors and sensors and actuators and motion tracking and a person, and it's actually kind of dangerous. Don't stick your fingers in the spinning thing. And so you need, anytime you're trying to build something, whether it's dangerous or not, you need to constantly be imagining how your system will behave, carefully observing what really does happen, and rigorously comparing those to each other. This is actually the scientific method. Sometimes you might feel like robotics or computer scientists, we're not scientists, but we are scientists, and we have to be watching our system and trying to guess. And you do this for many reasons, both to build your own understanding and to make it do what you want. There's this constant interplay between your mental model and then the real physical system, and you want to bring them into alignment. And when things don't agree, you really need to work hard to figure out why. Why is the thing spinning clockwise when it should be spinning counterclockwise? Or why don't I feel like what I should feel? Why is the thing crashing? And then you do more experiments to gather more information to improve your understanding. And throughout, this is really an active thought process. This is not just sitting there watching the latest show on Netflix and then where you might fall asleep. This is like intense paying attention and thinking curiously and aggressively wondering and getting pissed off when your system doesn't do what you thought it should do. I'm going to give you a random example of something I have a lot of confidence in, and that's Newton's second law. And I imagine you've learned this maybe multiple times in life, and you probably think, okay, Newton's second law, F equals ma. It's not just any F equals any M times any A. It's, I have a mass like this wooden ball, and we can take the sum of the forces that are acting on it. So like it's feeling its weight due to gravity, and it's feeling little forces from my fingers on each side and the squeezing forces that I'm pushing in on it. And if I can sum all those things, and those are vectors, I can calculate, if I know its mass, basically how much stuff is here, I can calculate its acceleration. What's acceleration? Well, it's the first time derivative of its velocity, which is the rate at which and the direction with which it's moving around the world, which is the second derivative of its position, which is very easy for you to observe, like where something physically is in 3D space. Some facts. Everything has mass. All robots, all cars, all car parts, all robot parts, they've all got mass. And unfortunately, nothing generates infinite forces. All of our actuators, they can make large forces, but they can never make infinite forces. So what does Newton's second law tell us? Well, if the left side of this vector equation is finite, and then I have to double integrate it, well, some things you already know. Objects cannot teleport, right? They cannot change position instantaneously. Something you might not have fully thought about the implications of Newton's second law, but velocity also then cannot change instantly. If you're driving down the street, you're going 20 kilometers an hour, or 25 miles an hour, or whatever, you cannot instantaneously speed up to 30 kilometers an hour or slow down. It doesn't happen instantly, it happens gradually. And that's part of what makes physical systems tricky to control. You don't have a lot of power. You're controlling the second derivative of the thing you often care about. And so this law, and many others, hopefully grow in your brain as things you can rely on. And that means you should never expect robot motions that defy Newton's second law, certainly not teleportation or step changes in velocity. And you should be really suspicious if your sensors seem to report them. Okay, so let's say you have Newton's second law and lots of other things in your brain, and you're watching your system. You will notice it's doing this weird thing. Maybe it's a jiggling in a way it shouldn't, or when you first turn on, your sensors read some weird value, and then after a second, they come to a normal value, or your hugging robot squeezes the person and doesn't let go, which can happen. You need to be relentless. This means don't give up. You must fight and seek these weird behaviors and figure out what's causing them. Little anomalies, that means weird behaviors, things you don't understand, they will come back and bite you later. It always happens. Now, of course, there's some random things that maybe you think aren't important. At least keep a list of them, like a written list of things I do not yet understand that my system is doing. And plan when you have that mythical free moment, as Max Mintz likes to say, that you will come back and look at them. And when other things start going wrong, look at that list and say, maybe there's some funny interaction, because any aspect of something you don't understand in your system is an indication that there's room for some error or problem or behavior that's you can't control or explain as a scientist, as an engineer. Okay, so how do I go about figuring it out? My system's doing this weird thing. Well, you need to act like a detective, like you see on television, or a doctor trying to diagnose an illness. And that means look at the clues, look at the symptoms. This is, again, this careful observation. Look at exactly what your system is doing. And the way it fails will tell you what is happening. Things don't fail in just one way. Someone tells me, that thing we talked about, it doesn't work. I say, okay, it didn't work, but what did it do? How did it fail? That's the rich detail, the guts and glory. And that will help you sort out what it's really doing and why it's doing that. And unfortunately, I'm sorry if I'm the first person to tell you this, robots are stupid. They do only exactly what you tell them to do. And that means if it's doing the wrong thing, you, the programmer, or someone else on your team, or the engineer, probably told it to do that wrong thing instead of what you wanted. And I know that's really frustrating, but this is, again, bringing in your mental model into alignment with the real system. It often is helpful, I didn't emphasize this from the beginning, but to break your system into smaller modules and test those. Identifying these interfaces between components is useful in design, makes an overall simpler design, and especially when things aren't working, you can check each individual piece. Like, I assume this amplifier is delivering the current that I want, and I assume that this motor is outputting the torque. And I assume that this sensor is measuring the applied force. And if any of those is wrong, obviously the entire system of those things put together is not going to function. Another solution that I like, and it is a little silly, but it works quite well, is to talk to a rubber duck. And this is not an idea I invented, but I believe in it, rubber duck debugging. So your first step is to find a rubber duck like this one. We give these to the doctoral students in our PhD program here at the Max Planck Institute for Intelligent Systems. It's our International Max Planck Research Tool for Intelligent Systems duck, because everyone runs into issues with their system at some point. And so you take your duck and you put it on your desk and you say, duck, I'm having a problem with my code. I'd like to go over it with you. And then explain to the duck what your code is supposed to do. Go into detail, explaining it line by line. And at some point, you will be telling the duck, so here's where I measure the sample, the value, and I square it, and I add it to the, and you will realize that that's not what you did, that you were calculating velocity, but the parentheses are in the wrong place, and you squared after the sum instead of the components before them, and that explains, and this is actually consistent with the data that you were noticing, where when I move left, right versus up, down, things behave different, and I don't know why that might be. And the duck will be very happy that it was able to help you. And this is not magic. This is human psychology. Why does this rubber duck debugging thing help? And if you don't believe me, you have to try it. But as I already mentioned, human brain works very different from a computer. In fact, the process of learning to program is the process of learning to think very literally and precisely. And for some of us, that comes easily, or some aspects come easily, but we're all still human. We are no computer. No matter how good at whatever you're doing, you still have not quite perfect computation in your brain. And so there are often, not always, logical errors that contribute to bugs and problems in our code. And the computer just literally just does exactly what we tell it to do. And so when you talk to the duck, you slow down. You have to tell it, you become more exacting because you have to slow down to speak. And you also have some perspective taking. You know this duck doesn't know much about your code, and so you explain more thoroughly and more exactly than you would if you were simply looking over your own code. So this is almost like a tool for yourself. And of course, if you don't have a rubber duck, you can use other things like a plant or a pet. I would caution you, though, against using people. You can, but I would first talk to a duck or something else, non-human, because many of these bugs can be found just on your own. All right, that is the end of my first of the 6 topics, and I'd love to take a moment, and Manuel, if you want to moderate, if there are any questions that the audience has at this time, the live audience, either about the motivation, the fact that creating these systems is difficult, or this first suggestion about thinking actively.
So it's time to do questions to Katherine, not your duck. Now you can do live. The Q&A system seems to be empty. The chat.
I'm happy to take questions from any of the panelists as well.
I can make a question, yeah. So, actually, this first topic is everything, right? It's not just about haptics. I know it's just understanding and starting in a new and you feel on your domain, you always have this problem, right? You are installing your packages of Python and they are incompatible or something. Okay, so that's, I think it's general. Huh? Everyone has this problem. And you feel, but for specific for Haptics, maybe what do you say is missing? It's missing like nice software packages. The problem is more about the mixture between the physical world and the software world. That is difficult to debug. What do you think it's really the main difficulty in the process or the state of the art? I don't know.
I personally think the main difficulty is real-time and physically interactive systems. So we can't simulate the things that we're working on. We can't simulate a human. That's a research project on its own. Even simulating friction and contact is crazy complicated. And we're using all these custom components that we buy from weird manufacturers and patching them together into novel systems. And you can't just Google it. I was talking to my husband about this last night. He's like, "Oh, yeah, just go on Stack Overflow." He develops apps sometimes, but there's no Stack Overflow. Maybe you can, or maybe you find someone else, but you're building first of kind, real-time systems with hardware and software. I see a bunch of questions came in on the Q&A. Manuel, do you want to maybe choose one of them or two?
I'll pick the third one because we are still in introduction. So are there home robots today which use haptics for interaction with humans?
Yeah, I mean, in research labs for sure. For commercial products, I am not sure. Haptics is like a whole spectrum. So like pretty much every robot has joint angle sensing. And so it knows its own pose in the world if it's correctly calibrated. And then some robots have torque sensing, especially if they are not back drivable. I didn't show any robots like this because we don't tend to use them. But I have in other projects and in the course I used to teach, we used this old Puma robot. Or actually, maybe I did show one torque sensing robot. But if a robot has a force sensor at its end effector or torque sensors at its joints, then you could say it has a rudimentary sense of its effort. So that could be haptic feedback. And yes, there's beautiful work on force control and making and breaking contact, switching between different, yes, there are things in that domain. What's missing, what robots have almost none of, is tactile sensing. So your skin, basically the glaber skin on your fingers, which doesn't have hair on it, and it has 4 different kinds of mechanoreceptors. They sense contact and shear and vibrations. And then the hairy skin everywhere else on your body, it has less accurate but very broadly distributed sensation, and robots are numb everywhere. And even just the sensors that we do have are often really expensive and don't provide that rich of information. Maybe they don't provide it very fast. They break really easily. They're not robust. Fundamentally, we have to be contacting things, and we're going to maybe contact things in very different ways. The keynote this morning by Antonio Bicchi, I thought was beautiful because he showed the importance of softness, which is another aspect of robots that is often missing. If you're going to accidentally bump into things or push into things, it would be good to have some soft covering, and to have that soft covering be sensorized so that your robot would know where contacts are taking place and could maybe come into your kitchen and pick dishes up and use its arm to open something and put things away and physically interact with the world with more than just its tiny, tiny little fingertips. Manuel, do you think we should maybe move to the next topic? I'll stop 2 more times for questions. Does that seem like a plan?
Yeah, okay, if you know better.
Or unless you have another one.
I think there's one here because it's really on this topic, and I think you'll not come back. So this, one of the main problems is because you have this real world and software, and I think that's one question that's relevant. So how should one think actively when you don't have all the details? So when you have a large group project, in this case, you have the software, you have the hardware. So I think this is a methodological thing about the rubber duck. So how do you think about a large group?
Okay, yeah, I think in my projects, the people who are cooperating, yeah, we often have people with different expertise. They do need to talk a lot. And so maybe you and your partner need to talk to a rubber duck together. Or these interfaces that I was talking about really clearly define those interfaces. But at the end, yeah, if there's something that is not working, your whole team might need to sit down and talk together and be a collective brain, because the complicated systems we're engineering, no one of us is often able to be deeply in all the pieces. I do feel like a lot of the systems I've built, I have been able to have my brain around pretty much every part. I don't write the code anymore. I'm not soldering the circuits, but I always try. Our demos, I'll talk more about this later, and interact with them and talk to my students and my team. But yeah, I guess that is a challenge, and therefore, yeah, you need to talk to other people, not just in one brain. Okay, shall we move on, Manuel?
Yeah.
Yeah, please, and please keep the questions going. I really appreciate it. It's nice to have it be a conversation even through Zoom. Okay, so that was my first of 6 strategies. Number 2 is plot. Plot. I love plotting. So you talk to the duck couldn't solve your problem. What do? So looking only at the output, like where your self-driving car drove, or how the hand grabbed the object, or what classification results you got, it's hard to tell what's happening when you're only looking at the end result. And so correcting some subtle problems inside can enable major improvements in your overall system performance. And so when your system's not working quite the way you want it to, or as well as you want it to, you need to gather as much information as you can so you can diagnose and fix it. And I think plotting is really important. Alexis Block says, plot everything. Maybe not absolutely everything, but really you can plot a lot of stuff and understand it. Why does plotting matter? I don't like plots. You do, actually, you just don't know it. Visualization is incredibly powerful. Humans have a brilliant system for interpreting visual input, and I know all you computer vision people know what I'm talking about, so you should let your brain work for you. And Felix Wichmann is a professor at the University of Tübingen who studies visual neuroscience. I heard him give a talk a few years ago, and he said, we have a majestic instrument for visual perception. I like this phrase, majestic instrument, so we should use it. Of course, when your system is running, you can also display things in real time, but as a human, it's hard to watch everything and really understand. And sometimes that very act of displaying slows your system down. So you may think, okay, I'm going to print f the joint angle 1,000 times a second. That printf will prevent your code from executing 1,000 times a second. So you can't, in the sensing and displaying and debugging, you don't want to be disturbing the very real-time process that you're trying to observe. And that's why I think saving data and plotting it afterwards, you really expand the amount of time you can have to understand and interpret and really look at the details. And so I wanted to show a really fast example. Here again is that phantom haptic device. And this was for a homework assignment in the robotics class that I used to teach at Penn in the Grass Lab. And I just moved the tool through a bunch of locations, and I clicked the button and I saved these encoder counts. And if you can look at those numbers and tell me anything about them, maybe you can first, at the first column, and see the numbers are going down, plot them, right? So the blue one is the first column. You see it does have a downward trend, and the other two are kind of oscillating around their values. These are over time. I wrote a word. Can anyone tell me what the word is that I wrote just from looking at the signals over time? No one can, I don't think. It was the word phantom. This is now the encoder counts, and it's curved because it's in joint space, not in the end effector Cartesian space, but you can still read the word because locally it's approximately a linear transformation, and you can just really quickly see what's happening. So plotting signals against one another, like, wow, that's something I could perceive in 3D space, and I can immediately make sense of it. I didn't put access labels, they're in encoder counts, but these are not like figures for paper, they're just debugging. You don't have to always be so proper. If you're going to show them to someone else, maybe you put some labels on them. What kinds of plots can you make? There's so many kinds. Gather data when your system is misbehaving, is doing the thing you don't want it to do. Plot the values over time, variables versus other variables, like I just showed you, looking at the internal states versus other states or variables. You can create histograms, and you can also use a third dimension. I just showed you 2D plots. You can allow rotation, animation over time, or color to really try to pack a lot of information into these visualizations. I'll give you a little case study. This is actually from when I was a postdoc with Alison Okamura at Johns Hopkins. We were working on, we thought that prosthetic devices should give proprioceptive feedback, but we didn't yet have good prosthesis devices. We didn't have any way to provide it. So we created a model system where the person kind of thinks they're moving their own finger around, but we put a geared DC motor. So this is like a very high control authority motor that can really drive your finger wherever it wants. And then a force sensor, so we can measure the force and we can control the dynamics between the force you exert and the movement we allow you to feel. And so we could simulate lots of different kinds of prosthetic fingers, basically. And so I programmed a controller, a PD controller, where I knew the trajectory, the theta and the omega, the angular velocity that I wanted the user's finger to undergo as a function of the force that they had been exerting. And I was testing my system. I thought, oh, this is really great. And all of a sudden, I started noticing, I feel this weird click. Like every once in a while, I move my finger. What is that? That's really strange. And so I recorded some data. I caught it on the first test. You see here at 4 seconds, there's this little glitch. So what do? You zoom in on it. And there's this like data point that's out of line. Now you remember Newton's second law. This thing has mass. It doesn't teleport and teleport back. So there's some problem, some weird thing going on. And I didn't want this thing to keep doing this. So I said, okay, how can I figure this out? And you like I said, you start paying attention to the clues, the way it's failing. And so I measured the distance from the angle, the error, and I found it's 1.8 degrees. And it was consistently 1.8 degrees. Okay, why is my data, I'm getting these values 1,000 times a second, and every once in a while, boom, 1.8 degrees wrong, and then it comes back? That's weird. So I did some math, and I looked at my encoder, and I figured out that it was exactly 256 counts on my encoder, 2 to the 8th. So 1 bit of the encoder count was just randomly flipping 0 to 1. It turned out this was a known issue with the board that we were using. This is not something I programmed wrong. This was like a known error, but I could fix it in software. And once I did that, then the data points would come right in line like we would expect, no teleportation, and I could carry on with my experiment. So here, this was the old velocity plot. We're going along and we have a minus like 1700 degrees per second and then a plus 1700 degrees per second. That doesn't look so good. And we replotted, here's our new velocity. So I ask you, curious audience, did we solve the mystery of this click? And I hope you say yes, we solved the click. But does that plot on the right look good? Are you happy with it? Should we just go filter it? I would say that we solved the mystery, but we also found another mystery. And so I don't know if that plot on the right looks good or weird to you. It looks really weird to me, but I've become rather suspicious in my old age. Here, let's zoom in again and look at it. Those little spikes, you see these extra spikes on top of like the main signal. You should be aware of unexpected patterns. So patterns that are normally here, I wouldn't expect much of a pattern. Certainly the human's not like speeding up every like fraction of a second and slowing back down. That's totally outside the bandwidth what a person could move their finger back and forth. So, and these spikes are not just random noise. They're very systematic, and I should not just filter them out. And if you zoom in on just one, this is one of these up here, you notice it's coming up from a baseline of about 35 up to 70 degrees per second. Sorry, that should say degrees per second, not degrees. So these spikes are about twice the value. That's weird. And that even happens positive, negative, like what is going on? The mystery deepens. So if I look at it in the data points, the individual positions, you see it much better. We were looking at the derivative of our position signal. And here's the actual position signal. And you see it's like a disjoint line. Again, Newton's second law, things don't like instantaneously change velocity and then go back to their old velocity. Like that doesn't make sense. That shouldn't happen. What could cause that? Nothing. That's not physical. So plotting these position measurements just as dots shows the same disturbance. And this was my fault. This one was my fault. I had made the bad assumption that my servo loop, this thing that runs 1,000 times a second, was executing at a constant rate over time. And I made that assumption because the lab that I did my PhD in at Stanford used real-time Linux, RTAI, and we could really depend on things. And this demo that I'm showing you now is programmed in Windows. And well, Windows is not a real-time operating system, but I'd never had to really grapple with that shortcoming. And so what I did was I added what I would call a time sensor. I started querying the processor clock when I sample my sensors. So I have my position sensor and a force sensor and a time sensor, like how much time has really passed since the last time my code ran. And then it was supposed to run 1,000 times a second, so 1 millisecond. And you see on average it was a little less, and then periodically, very systematically, something from Windows was interrupting it and taking about twice the amount of time that it was supposed to. But I was blithely assuming only 1 millisecond had passed and divided my change in position over change in time by a constant, which was a bad decision. And so if this was my old data, once I use the correct real time instead of assumed time, the plot becomes physical and nice and real and beautiful. I went a long time without any data, but that's fine. I don't need to have a sampling rate that's exactly even. And then if we take this back into the velocity signal, here on the left again is my velocity signal with those suspicious spikes. And now when we use real time to do our differentiation, it becomes much, much, much nicer. And here, if you're not familiar with encoders, they have a discrete number of, it's a discrete sensor, so they're very noise robust. And in every time step, you'll have an integer number, 1, 2, 3, 4 encoder ticks go by. So that's why we have this stair stepping, which is really what we would expect. So I would say, did we solve the mystery? I would say yes. We did. This velocity looks really good to me. And that actually, I hadn't noticed it, but after I got rid of the clicks, these were causing little vibrations that I could feel. And when I did this, there were no more vibrations. Just a few more plotting tips. Be careful of filtering signals, whether it's over time or space. It's powerful, but take a look at the original signal. Just don't plot. It's like salting your food before you taste it. There's not a one size fits all. You should really look at what is there. Noise is in the eye of the beholder. And so take a look at what you're handling and what happens. Give units. Units are really important. I know I'm a mechanical engineer and units give me grounding. I have trouble when like gravity is defined as just 20. But in access labels, us engineers, people who know the physical world, we need units and measurements. Radians are a common unit that comes up in robotics a lot when you're thinking about the orientation, you're doing angles. And you should know they're unitless because they're a ratio. If you never understood what a radian is, you probably did, but or maybe you long ago knew this. A radian is the ratio between the arc length on a circle, any size, divided by the radius. And that's just beautiful. That's why radians are a ratio of length over length. And but if you're being nice to the reader, you can say radians and not just 1.2, but truly it is just 1.2 or some whatever. When you're converting units, I know this sounds trivial, sounds like middle school, but I cannot tell you the number of times that unit conversions have caused problems. You're allowed to convert units because you're multiplying by two things. You can make an equation like pi radians is equal to 180 degrees, and I can divide them and now have this thing that's equal to 1, and I can multiply 1 by anything without changing anything. And I do it so I cancel the units, and it comes out. If you can't remember that pi radians is 180 degrees, you can remember that if I fit a hexagon in a circle, we basically have 3 equilateral triangles on the top. So that arc length along the top, that's about 3 and a little bit. 3.14, 159, 26535, yada, yada, yada. So these like tangible metrics, when we're raised to really deeply understand what you're working with, they help you avoid stupid mistakes. And then lastly, when you're plotting in 2D or 3D, especially position, make sure that something that's shown in the X or the Y or the Z direction is showing at the same aspect ratio. So like a circle should look like a circle. Something that's a 45-degree angle should be at a 45-degree angle. And if you stretch it or compress it, your eyes can't use the judgments that they're used to making when you look at things in the physical world. And here I have just one more quick case study. In 2012, my husband and I, that's Jonathan Feeney there, we went skiing in Whistler Blackcomb after a conference, and he used this app to record GPS data of where he skied. And then later I asked him for the data for a demo for my dynamics class. And here we have longitude, latitude, and altitude. And you already know we plot them over time. Here we have a course of hours. We can plot them against one another, and you see this plot on the right-hand side. That's the trajectory. Oh, I forgot to point out, at Whistler, Blackcomb, there are two mountains, and there's this gondola that goes between them as one of little lifts, like chair lifts that you ride up and then you ski down, in case you haven't skied. So here is a plot of the skier motion in 3D. And you can see the trajectory. But a few things to notice. It's like stretching and changing in different directions. This is not so lovely. Also, the latitude and longitude don't let me know the actual angles and heights. The height is stretching as I'm rotating it. So this is kind of bad news. It's hard for your brain to process. So now I converted all the coordinates, latitude, longitude, and altitude, all to meters. And then I use MATLAB. Of course, there's many other programs I use in MATLAB called axis equal, so that 1,000 meters in X and Y and Z is all equal. And then axis viz 3D makes it show like a rigid object, so it's not growing and compressing. And then we animate over time. So now you can see this day that Jonathan and I spent skiing in Whistler Blackcomb. He's the little black dot. You can see him riding. That was a really good lift, apparently. I think we stopped for lunch. And then he's coming over. And then here, oh, that's the gondola ride. And I want you to notice how much better you can appreciate the movement that was observed by watching it over time and in 3D. That's the end of the day skiing down to the bottom of the mountain, and you can really see the structure and the shape. It stays at a constant scale. If this was interesting to you, you could probably much better analyze the movement that happened by treating it in this way. So that's my second module. This was plot, plot, plot. And I put a summary here, but would be happy to hear any questions, comments, that you might have.
I think we can use one question from the previous. So Benjamin Bohr. So you're talking about debugging, right? But in a way, you get using your intuition about debugging. So, but there are some other people, like they come from formal methods, and I think Benjamin is one of them. So I'll just ask his question. So, have formal reliability and systems engineer techniques commonly used in aerospace crossed your desk? I suppose you're assuming he's asking, can we do formal verification of this system, automatic tools for software verification? Can you use this type of techniques to achieve the same goal as you're suggesting to do as a nice manually?
Yeah. Benjamin, thank you for the nice question. And of course, I'm limited in what I know about, and I'm getting old, so there are wonderful tools out there, but I have two kind of responses. So why I think those kinds of very formal tools don't often work so well in robotics. So we are building new systems. They've never been built before. And so going to the effort of having like a formal verification system really early in development, I think doesn't make sense. So we can learn elements, we can take elements like unit tests or things like that. And of course, the scale of the project, I'm talking about smaller scale projects, few people, 5, 6 people maybe, and with mechanical and computational and electrical elements with human component, which is why I think it's really, I think nothing takes the place of a person walking in and hugging the robot or playing the game with it. So there are limits. The other goal that I have beyond my goal is not only the product, to make an excellent product. The later we get, if we're creating a database or a software repository for many other researchers, then yeah, we should probably get to that maturity level. Then we're really sure what we built is worth that. But my other goal that I'm serving is education, that the people who are developing the system, I want them to not just get it to work somehow, but actually understanding all the things that it does. And of course, they could also do that by writing tests and formal methods. I think these kinds of things that I'm showing will benefit people who want to create robots in the world, because you build a better model in your mind. Yes, it is manual, but I think I don't know another way to get these physically interactive human robot systems working in a way we want to have them work. Manuel, do we have another question you want to handle?
Yeah, I think we can have one or two more. So one is from Lucas Manueli. So it's okay. In short, It's like you can debug things that you have an intuition, but if you are debugging the embedded dimensions or some autoencoder, how can you debug that?
Yeah, so in the last few parts, the final part of my talk, I will present more things that are relevant for there. That is actually also an aspect of tools that is how well they lend themselves to debugging, so interpretability of your system can be considered as a benefit and a drawback when it's not as good as you might want. I think explainable machine learning is very interesting to many people for that reason. But maybe there will be some answers in the last 4 points I want to make. But yeah, sometimes things that you don't have a lot of intuition in a way because you don't have the knowledge or because that system is a black box, and that's very frustrating. Yeah, maybe Manuel, I should go to the last components, okay, and then we can take more questions. I'll take questions on any part at the end, but I want to make sure I don't go over time. Cool. All right, so now number 3, and maybe this is an answer for the last person's question, getting help. So you're not alone, you're in a team. Maybe you made these plots, you don't know, the duck didn't help you, I made these plots, I don't know what my system's doing. So we want to master these concepts. And the analogy I use is that you want to master them like they're a physical tool, like a hammer or let's say a hammer. You want to be able to grasp them securely with your brain, to be able to use them with power, to be able to exert force and do useful things with them. And certainly if concepts are like slipping out of your fingers, that's dangerous. You can break something, especially if this robot's going to come near people as doing surgery. It could go unstable, or you need to invest the time and energy. I mean, this is obvious for students, but to really understand these tools, studying, learning, getting resources, we learn over our entire lifetime. All of the professors, all of us, our brains are like muscles, and we have the ability to learn new skills. Don't let someone tell you, oh, you're a computer scientist, like that's physics, don't worry, or vice versa. You're a mechanical engineer, you can't understand the software in our project, the code. You can, you just might have to work a little harder and get some background, go take another course, take an online class. And this one's really important and hard, I think, for some people to accept. Don't be ashamed of being confused. And don't try to hide it, because there's really no escaping your confusion. Maybe for a day or two, you can go study and learn on your own. But in a team or in a project, it'll quickly come out that you don't know what you're doing or you're confused. And it's not really something to be ashamed of. Actually, some of the people I've worked with that I'm most impressed with would ask questions, even simple questions, and to try to make sure they weren't confused. They were doing this active thinking to always stay in mastery of what was happening. And if they got confused, they would just ask, and it's so powerful. So seeking resources, talk to other people in your team, other people around the world, asking thoughtful questions. If commercial products are involved, read their documentation, obviously. And for hardware, there's usually engineers who work at the company. And if you can get to them and talk to them and send them your plots, send them videos of your system, they can help you figure it out. And sometimes you show them new things about their hardware that they never knew. Sometimes they then go fix their firmware to make it better for other people. And that's also powerful. And lastly, I recommend you take time away from hard problems. If you just sit and bang your head into something over days and days, you will lose efficiency. So have other threads of your projects, come work on something else, make figures for your paper, write some of the paper, give your brain time off. It will keep working on these things in the background. You might also wonder, who can help me? You said get help. Talk to other people, explain what you're doing, think about their questions and their comments. I know this is difficult in very competitive areas of research where you're afraid of people stealing your ideas. You need to have at least some core team of people around you that you can trust. And to talk to, because otherwise it's really hard to create new things. And don't just assume that someone can't help you because they don't know anything about autoencoders or force sensors. You don't know everything they've ever worked on. And sometimes there's deeper similarities in their background and what you're working on than you know, or maybe a fresh perspective. Actually, I think this is why research thrives with new people, PhD students, young people coming into the field with a fresh view. It'll help you see things that people with more experience don't. I also want you to realize that diverse teams make great contributions and often bring valuable insights. And know that all of us, me included, we have biases about gender, we have biases about race or country of origin that we might let affect us, whether this person can help me or not. This is my team from last November, before COVID-19, when we were allowed to be this close together. We come from tons of backgrounds, tons of countries, many ages, many nationalities, many genders, and I see connections in my team. I assign technical triplet meetings when I'm traveling or busy and don't have time to meet, and I put together 3 people who talk together. And it's not just all 3 computer scientists or 3, I make them different every time so they can, based on the current trajectory of their work. And I think it's beneficial. So give other people a chance to talk about your work, and volunteer to help others. You'll build your own skill set. It's very rewarding. And occasionally, my team, we've had a problem we couldn't solve, and I have offered a cash prize, like $100 or 50 euros to solve it. And that can be very motivating to some people, so you can consider that. Lastly, in this Get Help, you might be sitting there thinking, I need to solve this problem. It's not working. I need a way to know when the person's handing the object to the other person. And here, the techniques of brainstorming are really helpful. A long time ago, I interned at IDEO, which is a design firm, a really like world famous product design firm. And they have these 7 rules of brainstorming. And I'll just go through them quickly, but they work extraordinarily well. Defer judgment. It is way easier to criticize other people's ideas than come up with ideas of your own. Just put the judging later. Encouraging wild ideas. This is how we make the biggest innovations. Think crazy. Build on the ideas of others. Listen to the other people and say, yeah, and what if we did that? Stay focused on the topic. Don't start talking about the elections or COVID or your project. Try to stay mainly on the topic. Have only one conversation at a time. Be visual, write it out, take notes, and go for quantity. Try to get as many ideas as possible, because that's the best way to have a good idea, is to have a lot of ideas. My 4th point would be to demonstrate your work broadly, to show it when you're ready or still in the process. How can I make my work better? Try to prepare for diverse users, diverse situations, diverse objects, diverse intersections that your self-driving car will run into. And know that, when you only have a limited training set, you're probably overfitting. And so testing, I'm talking now about human and physical interaction systems with many, many people. And this is before we're actually doing any evaluation, anything that would be in a paper. It says piloting. Of course, you want to follow any safety rules and make sure they understand that this is totally voluntary. Even if they're your friend, they don't have to let you put that thing on them and try this exoskeleton. But adapting things to many different people, many different users is challenging. And it's nice often to give them a contrast, like with and without the key thing you're working on, like this extra capability, so they can try both versions. Be ready to demo at any time. And here, a personal story. When I was a grad student sitting in my lab at Stanford, and I was applying to faculty jobs, one day, Vijay Kumar knocked on the door and came in. And he was at the time the chair of mechanical engineering at Penn, at the Grass Lab, where I ended up working. He's now the dean of engineering at Penn. And he was like, hey, you applied for our faculty job. You're Katherine, right? And I said, yeah, do you want a demo of my research? And it's definitely not why I got the job, but be able to show your stuff anytime, some version. Of course, if your system's not working, have a video, and listen to what they say. Listen to the questions they ask. If you can, take your work to conferences. So in Haptics and HRI, sometimes in robotics, we have demos. You can bring it. And then the great thing is colleagues from around the world can come and try your system and give you feedback. Another really important person is your boss or your advisor, the judge in a competition. They're almost always going to break things. It's a special talent that professors have. It's normal, and it's because they know too much and can really fast find the weak points. They know where things will go wrong, and so learn from that. I also would counsel the advisors here and everybody else, all of us, we get really confident of beliefs all over time, but I would always recommend leaving room to learn new things and be surprised. Don't be 100% sure. As my great aunt Winnie said, say your words softly so they are easier to eat later, because sometimes you'll be wrong, and that will be really surprising and interesting. And kind of in that vein, there are times when you should test what everyone believes. Even if everyone says, oh yeah, that never works, you should always do it this way. If nothing else is working, go ahead and violate that common wisdom in it. One experiment is worth a lot of expert opinions, maybe not 1,000. And those are the times when we make big jumps forward. So be bold, but respectful. If you don't have data, probably the wisdom is right. Okay, just 2 more points and they're pretty fast. Prepare for the unexpected. I'm talking about all these physical experiments. Try to automate and document your processes. You, the human, the operator, the researcher, the engineer, you're the weakest link in the system. Make sure it's turned on. You need to have power and ground. Your process needs to be running. Buy backup things, especially once you know you're going to need it, have 1 or 2 extras. I know this is tricky when you have limited funding. There have actually been times when I've spent my own money to buy extra components because I personally didn't want to have to invest the time that would be needed to, or be where I designed around a component and couldn't have it, because maybe there was only one and now they don't make that thing anymore. But yeah, delivery times and availability of special components can be really frustrating. So have some extras if possible. A few more things, collect extra data. If you're already collecting data, it's precious. Just get more, a few more than you thought you would need. Don't delete things. Just comment it out or archive it or version it. You might need it someday. Back up everything a couple times, and you never know when your water bottle might open in your backpack when you're flying to IROS in Macau to give a keynote, a plenary, and like drown your laptop and kill all your files, everything, and you have only a couple days to present, create a whole new presentation. And yeah, so know how to access your backups. That did happen to me, by the way, last year. Last one, be positive. I don't know if you're discouraged or encouraged by the things I've been telling you, but I think it takes optimism to be a researcher, especially when you're dealing with these complex systems. Laugh a lot, not at other people, but about yourself and things that go wrong, and making clever jokes and looking for the humor. It will really help you and your team make progress faster. Get some exercise. You can see my bicycle behind me. I bike to and from work every day unless it's really pouring rain. It's really good for your brain and body. Take a walk around the block, get some fresh air, unless you're in lockdown, in which case stay home. Be grateful and polite. Thank people who have helped you. If someone is not nice to you, apologize and assume they're having a bad year, bad day, bad month. It probably has been a bad year for all of us. And lastly, take vacations. They're really important. And this is actually very German. In America, we work so hard. I'm American. Germans have 30 vacation days a year. And it's good to take time away. You get new ideas and you have more energy. And when you come back to your robot or your code, you have new ideas. You will long-term be more efficient than if you just work. These are my opinions. Maybe they're useful to you. Here's my summary for section 3, and I'd be happy to take questions if anyone has any or comments. Manuel, I saw a lot of questions coming in. Do you want to choose one?
Yeah, some of them were already. So maybe about you talked a bit about backgrounds. So maybe you can take this one. So have you noticed differences in how researchers in electrical engineering, computer science think about these problems and how they debug differently?
Yeah, and I'm often trying to get them to teach each other the techniques from the different disciplines. So no one can, I think it's hard to be an expert in all the things. Even if you double major in mechanical engineering, electrical engineering, or computer science and mechanical, we're going to have gaps and things come up. I have bioengineers, I have cognitive scientists, neuroscientists, I've had medical students, residents, people with truly different backgrounds, high school students. And there are differences. You should use the tools that you're learning and be open to learning other ones. But I think often the students and team members who gravitate towards my team are people who have already had interdisciplinary experiences, like they got a master's degree in robotics, or they worked across fields. They did a bachelor's degree in material science, a master's in mechanical engineering, then wrote software in industry and want to do robotics and learning now. So I think you can collect strategies and teach each other the tools from your discipline, your background. This is personally why I like having interdisciplinary teams. If everyone on your team is an electrical engineer, everyone's a mechanical engineer, the number of solutions and ideas and projects and problems that you work on is going to be somewhat more limited than if you have team members coming from a bunch of different backgrounds.
Okay, one related to your record everything. I have a problem when I record everything, then I lose track. I don't know what version 17 was. So Eric Cosino made a question. So do you have suggested tools in your lab for reproducing issues for others and for talking with engineers elsewhere? So do you use GitHub, do you use other tools?
Yeah, we definitely do use GitHub, and I probably should be more explicit in how I tell my team members like what I expect and what to do. So maybe not record everything, but save versions and keep notes. I keep a lab notebook, like literally a notebook, and take notes in it. And when I was a grad student, I would even sometimes print out plots and code and put them here. Some people do it now, of course, digitally and keep a repository with versioning systems. Yeah, I think I'm best in just trying to caution you against throwing things out that worked to some extent, like keep a record, but you should talk to people who are more expert than I am about efficient, good tools to use for that. Manuel, do you have one more question for me? Or shall I wrap up? No, Manuel, he disappeared. So I'll just wrap up then. Thank you, everybody. Those were the 6 strategies that I wanted to share, which really were about debugging complex systems to make these interactive haptic robots. I again want to thank you, the audience, the organizers, many people who've helped me along the way, Jonathan, Georg, and Alexis for giving input on the presentation, and wrap up. So thank you all so much.
Thank you, Katherine. I think Manuel is.
Yeah, sorry.
Oh, okay.
There was a small problem with the connection.
No worries.
I lost 1 minute, so if someone can cover for me.
No worries.
Let me just thank you, Katherine. That was a wonderful talk and a tutorial, and really a lot of wisdom and a lot of very insightful suggestions for researchers in the broad area of robot learning, and then in the particular experiences that you've had with haptics. So thank you very much.
My pleasure. Thanks again for having me. Hopefully some of it might be useful to someone. Take care.
Thank you.